So this was one example, and it has the height h, and then the radius of the cylinder was r, and we also computed for the explosion vector field. X, y, z. We computed the flux, and we ended up with this result. Let me just write down the parametric representation. It's a function of u and v, and I'm only looking at the curved surface here, so it will be r cosine u, r sine u, and then a v. To pi, and then v is between 0 and the height h. So this will describe the cylinder, and we computed the flux of v through this surface here, and the result was r squared times 2 pi times h. I'm going to need this result a little later. But what I'm going to do now is that I'm going to motivate why it's so cool with Gauss's theorem. Say, and I'm going to do this by trying to compute, or in a spherical, we have a spherical shell, and it's centered at the origin, and it has the radius r. Let me just repeat to you from, I think, from a couple of weeks ago. We wrote down the standard parametric representation for this this sphere. We have a sphere like this. Have the z, y, and then the x-axis. And it is given as r times sine of v cosine u, then r sine of the sine of u, and then finally r cosine v. V here is, say, if you have a point here, then v is this angle here at the top surface. R is, of course, the radius of the sphere, and then you have that u is the angle with the x-axis of the projection down to the xy plane. So this is the standard, and if you take the limits for this, then you have that u varies from 0 to 2 pi, v varies from 0 to 2 pi, and then finally, not finally, this is it. It's on the surface. Okay, and now I'm going to take a vector field. and it's a function of x, y, and z. And it's tangent hyperbolic to y plus z squared, then plus x. And then it's e to, say, x squared plus z squared minus cosine hyperbolicus of x. And then finally it's sine hyperbolic of y plus x cubed plus z. The thing here is that this is pretty ugly. So if you should do, say, if you should find the flux of this vector field outside, out of the sphere here, out of this spherical surface, then you should calculate flux here. Why did I? Maybe I have space here to do this. Flux of V, comma FR. Yeah, we have our parameters, so you should integrate from 0 to pi and from 0 to 2 pi. And then you should take your vector field and you should put in your parametric representation. And then you should multiply by the normal vector, that is R V here, the cross product here, and then du dv. So even for just writing this down with this vector field here and this parametric representation, I probably wouldn't finish at lunch. And if I then should compute the integrals, that will be quite cumbersome. And even if you try to make Mabel do this, it will have a hard time doing it. So thank God we have Gauss, because let's try to use Gauss in this. Instead of computing this surface integral, let's compute the divergence of the vector field. So I should take the first coordinate here and I should differentiate it with respect to x. X is only entering here, so you get a 1. Then you should take the second coordinate and differentiate it with respect to y, but y doesn't enter, so you get a 0. 1 plus 0. And then finally for the third coordinate, you only have z here, so you get a 1. So the divergence is 1 plus 0 plus 1, that is 2. So you have this constant divergence. So, so according to Gauss, we get the result that we get the flux of V out is equal to the volume integral, that is, you integrate over the whole volume of the divergence, but this is 2, and then d mu. Now 2 is constant, you can put it outside, and what is left here is the integral of a 1. So this is simply the volume of a sphere. So the result is 4/3 pi and then r cubed. So you can actually do this rather complex calculation of the of this flux here just by mental computation. And this is nice. Now, this was an example of a constant of a vector field with a constant divergence. What if the divergence of the vector field is 0? Then if you have a closed surface and you integrate, or you look at the flux of this vector field out of the surface, you will get 0, because it is simply the divergence times the volume of that solid field that is a result. And there are many vector fields that have 0 divergence, and there's particularly one if you can write your vector field as the curl of another vector field. If you can do that, then the divergence is 0, because the divergence of the curl of a vector field is 0. And this is simply to prove. Just write down the components of these vectors and you will see it. And in physics there are many examples of fields that are divergence free. For instance, in fluids, if you have an incompressible fluid, now air is not incompressible, but water is to a great extent. And since water is incompressible, it has 0 divergence. Or, I should say, the velocity field. That is the velocity of the fluid particles, the water particles. They have 0 divergence. Now, I promised you earlier on that I would look at or I will apply the Gauss theorem to a surface with or an open surface. And I'm going to repeat. Yeah, sorry, I have to go back to this one. I will repeat this example now using Gauss. Yeah, I can take it up afterwards. So, let me just, I can write it again. I've seen it a couple of times now, but here you have your cylinder, X, Y, and Z, and you have the height H and the radius R. Now, if I look at the flux out of this cylinder, there's the boundary of my solid omega. Then I get a flux out of the top. And I get a flux out of the bottom. And then finally, I get a flux of the curved surface. Previously, in this example that is on the back blackboard board, I computed this. I can write it down here. It is 2 pi r squared h. Now this flux here I can compute using Gauss. So this will be equal to this volume integral over my solid field sigma, and then the divergence of the vector field. Now, my vector field, remember, my vector field was the explosion vector field, so it was simply x, y, and z. And the divergence of this explosion vector field is 1 plus 1 plus 1, that is 3, when you compute it. And being a constant, I can, or let me just write it down. So this is the integral over the solid field, and then the divergence. And again, I can put the 3 outside, and what is left is the volume of this cylinder. And the volume of the cylinder is the area of the base, that is p r squared, times the height. So this is equal to 3h times pi times r squared. Okay. In this equation, I have this side here, which is 3 times this one, and then I have the flux through the curved surface, or I should say I'm interested in computing this by this method. So what I need is that I need to compute the flux through the top surface and through the bottom surface. Let me start by computing the flux through the top. And this will be the top. I have the vector field, but I have to evaluate the vector field at the top, so I get the coordinates x, y, but the z coordinate is h, constant. You are at this top surface, and the height here is h. And then I need a unit normal vector at the top. And this is, you see here, it's pointing in the z direction, so it's 0, 0, 1. Now this is a plane integral, and well, normally you would need some kind of, or I just write down here, d mu. Okay, like this. Because when you do this, this vector field here, let me write this. This is x, y, h. It's the explosion vector field dotted with 0, 0, 1. And when I perform this dot product here, I just get an h. So this is h and then d. Again, you can put h outside, and you get this integral over the top surface of d mu. That is, you have a 1 here. So this is simply the area of the top surface, this one. And now the area of the top surface, that is pi times r squared. If I look at the flux through the bottom, again I get the area or the integral over the bottom, and then the dot product between x comma y comma 0. And then here you have, say, where do you have it? You have here you have this normal vector. Down here you have this normal vector here, and this will be 0, 0, minus 1, and then d mu. But you see this dot product here is 0. So, and then you get 0 times the area of the bottom surface, but you get a 0 here. And now we have the left-hand side in this equation. We have this one, and we have this one, but we miss this one. So we should take these 3h pi r squared, and we should subtract this one, and then we get 2p, or 2 pi r squared. And this is actually the result we got when we did the calculation. This calculation wasn't that difficult, but this calculation here is even easier. You can do it mentally, hopefully. So you should have fun with the Gaussian theorem this afternoon. There's one thing more I want to tell you before we end this session, and this is about volume expansion. And I think I'll do it over here. Volume expansion. And we're looking at, I write down here, when a surface F floats along the flow curves for a vector field V, then when this surface floats along with the vector field, it sweeps out a volume or a spatial field. So I write here, when the surface F, I just write again, F sweeps a spatial field I write it as omega. But now this is dependent on time. You're looking at flow curves, and you are going from time 0 to an arbitrary point in time, and then you look at this solid that is swept. Now, if I compute the volume of this, that is, I could write it as the volume of this solid space here, and this will be a function of time. If this is the case, then it applies that that the derivative, and this is only a function of time, so the derivative of this volume of this space here, and this is it is given by a parametric representation. This rate here, this change with time, and if you compute this at time 0, that is the initial point, then this is equal to the flux. I'm mentioning this here now because there's a problem about it, problem or exercise 2 this afternoon, but it is also used in the e-notes for theoretical purposes. So what I'm going to do is that I'm going to take you through a really simple example of this. So let me look at this situation. I have here a surface that is, I write it in this way, I have here the x-axis, and then this surface here is parallel to the y-axis, and then you have, it's also parallel to the z-axis. Like this. Now, this point here is, I just choose an arbitrary x, and well, not arbitrary, but I use the starting position 2, 0, 0. And then the width of this rectangle here is b. So this point here is 2, b, 0. This point here is, I use the height h. So this will be 2, 0, h. And this will be 2, b, h. So I have these 4 points. And I have a parametric representation of this. It is r uv, that is 2, u, v. That is, I've taken y and set as u and v parameters. So I have that u belongs to this interval 0, b, and v belongs to this interval 0, h. So this is the setting, and I'm looking at a particular vector field. That is, I'm looking at this vector field x, y, z is equal to x, 0, 0. So it's a vector field pointing in the x direction, and say the first coordinate is x. So I'm going to try to illustrate this this theorem here, and in order to do so, I need to compute the flow curves for this vector field. And the flow curves is simply defined as x prime of t, y prime of t, z prime of t, and then it is equal to x of t. That is, this derivative here of my flow curves is equal to the vector field, so that will be x of t 0 and 0. And this, from this I can immediately write down the solution. And I write it down for any point in this rectangle here. So you see x prime is 0, z prime is 0, so these are constants. And then initially they are at this surface, so the constants are u and v. So I have this representation for the second and third coordinate. For the first coordinate, I have this differential equation. X prime is equal to x. And the solution is, of course, the exponential function e2. And initially, this function is 2 at this surface here. So let's try to look at I take, say, at some later point, it's still a rectangle. It will stay as a rectangle because so this x value here is 2et, and this is still b, and this is h. So if I look at this volume here, then, or this field here between these two surfaces, then the volume of is simply this length here, and that is 2et minus 2, that is this length, and then times the width and the height of this box here. So I end up by 2et and then bh minus 2bh. If I then take the derivative of this volume with respect to time, then I get, this is the constant, so that is 0. Here I get 2bh et. And if I evaluate this this at 0, then I get 2bh. Oh, at 0, of course. Now this should equal the flux of my vector field out of this area here. But if you look at this at my vector field here, then the value of my vector here is 2, 0, 0. You should dot it with a normal vector that is 1, 0, 0. So this value is 2, and then you have the area of this surface that is b times h. So this is equal to the flux, in this case, of v out of this area. I won't say more about this special flux here. Do the exercises, but whenever you look through the e-notes, then you should remember that this is one of the things that is, or one of the elements that are used in the e-notes for motivating and doing Gauss's theorem. Okay, well, thank you, and have fun with the exercises this afternoon.